to the third part of Elements of Neural Network and Deep Learning. My name is T.M. Ganesh, and this is the third part. This presentation, like the earlier parts, is also based on the two courses I had done from Coursera, namely Neural Networks and Deep Learning by Professor Andrew Ng, and Neural Networks of Machine Learning by Professor Jeffrey Hinton at Coursera, two books. Neural Networks and Deep Learning by Michael Nielsen, and Deep Learning book by Ian Goodfellow, Yoshua Bengio, and Aaron Corwell. I've also used other material from the internet. So in our last part, in the second part, I had shown if you try to implement a logistic regression as a simple two-layer neural network, you would not get a very clean boundary. You would not get a non-linear boundary. You would just get a linear boundary. Okay, now in this part, we will look at the derivations of the equations for the most elementary and the most primitive neural network, which is a neural network with just three layers. There is one input layer where you have the input features, one hidden layer, and one output layer. So these circles in the hidden layer and the output layer are known as activation functions, and they can be they can be any nonlinear function. For example, the sigmoid function, the tanh, Relu, or the leaky Relu. A neural network which just has one hidden layer is called a simple neural network. If you have more than one hidden layer, then it's called a deep learning network. So let us look at these activation functions. These activation functions are typically non-linear, and some examples are shown below. Here we have the sigmoid function, which you have already seen in part 2. So the sigmoid function at 0, it has a value of 0.5, and for small values of z, it slowly increases and finally plateaus at 1. And similarly for values less than 0, it decreases, and for large values below 0, negative values, it actually plateaus at 0. And this is the tanh function. This has a very similar characteristics as Relu, except that at 0 it has a value of 0, and for large values of z, it plateaus at 1, and large negative values, it plateaus at -1. The tanh is generally supposed to have a better performance than the sigmoid. One of the reasons being that it has a mean of 0. And the last is a Relu function, which is also very commonly used in deep learning networks. Basically, for negative values, this Relu has a value of 0, and for positive values, it has the value z. So Relu can be represented as the max of 0, z. So if z was negative, it will be 0, it will be the max, and for positive values, it will be positive. Okay, so why do activation functions have to be nonlinear? Activation functions, that is the hidden layer and the output layer, generally have to be nonlinear. If we try to use linear functions in the hidden layer, then what happens is, and we are trying to do binary classification, then the neural network essentially reduces to being a simple logistic regression, and we cannot do complex things like generating nonlinear boundaries. So hence activation functions are generally nonlinear. However, linear activation functions are sometimes used if we are trying to do multivariate regression, where the output variable is continuous. Now let us take a simple three-layer neural network. So we have two inputs, x1 and x2, and a bias term. So the x1 term, we have weights w11 superscript 1, w12 superscript 2, w12 superscript 1 and w13 superscript 1, where the superscript denotes that these are the weights in the first layer. Similarly, the weights for the feature 2, let us assume we start with w21 superscript 1, w22 superscript 1, and w23 superscript 1, and we have the bias term. So the linear activation at the first hidden layer can be computed as z11 is w11 superscript 1 plus w21 superscript into x2 plus b1, and z12 is w12 superscript 1 into x1 plus w22 superscript 1 into x2 plus b1, and z13 is w13 superscript 1 into x1, w23 superscript 1 into x2 plus b1. And at the other end, we have the activation function. This can be any nonlinear activation function. in this simple case, I've used the tanh h as the activation function. So A11 is tanh h of Z11, A12 is tanh h of Z12, and A13 is tanh h of Z13. And in the output layer, we can calculate the linear activation Z21 as W11 superscript 2 into A11 plus W21 superscript 2 into A12 plus W31 superscript 2 into A13 plus B2, where the superscript 2 denotes the weights in the second layer. And since we are trying to do a binary classification, the activation function A21 is a sigmoid activation function, and A21 is equal to sigmoid of Z21. Now we can rewrite this in matrix form, where Z1 is equal to capital Z1 is equal to this vector Z11, Z12, Z13 here, and we can rewrite this right hand side as in matrix form as W11 superscript 1, W21 superscript 1, W12 superscript 1, W22 superscript 1, and W13 superscript 1, W23 superscript 1 into X1 and X2 plus B1. Basically this is just a matrix, so basically Z1 will be equal to the multiplication of this into this plus B1. So it will be basically reduced to the same value, W11 superscript 1 X1 plus W21 superscript 1 into X2 plus B2. So this Z1 will, once you multiply and reduce this, it will be the same thing. So similarly for Z12 and Z13, and capital A1 is the activation function at the first hidden layer. This A11, A12 and A13 a vector of a column vector, which will be tanh h of Z11, tanh h of Z12 and tanh h of Z13 here. And in layer 2, again we can rewrite as capital Z2 is basically in matrix form W11 superscript 2, W21 superscript 2, W31 superscript 2 into Z1, Z12 and Z13 plus B2, and at the output layer A2 is equal to A21 is equal to sigmoid of Z21. So we can rewrite this in matrix form as Z1 is equal to W1 into X, where W1 is the weight matrix and X is the features plus bias. X, actually you have M trading samples, that is no, but I'm just taking it as 1, which is represented as X, and A1 is tanh h of Z1, and Z2 is W2 A1 plus B2, and A2 is equal to sigmoid of Z2. Basically I'm just rewriting these equations here. Now let us try to find how to get the derivative of tanh hx. Now we know d by dx of Ex is equal to e power x, and d by dx of e power minus x is e minus of e power minus x, and we know the sin hx is given by e power x minus e power minus x divided by 2, and cos hx is e power x plus e power minus x divided by 2. Hence if I take the derivative of sin hx, if I take the derivative of this, it will essentially be e power x, and if I take the derivative of this using this result, it will basically be e power x plus e power minus x divided by 2, and d by dx of cos hx will be sin hx. Now let us look at the division rule. The division rule is given as d by dx of, if you have f of x divided by g of x, it is given as the denominator g of x into d by dx of the numerator f of x minus the numerator f of x into d by dx of the denominator divided by g of x the whole square. Now we can find the derivative of tanh hx. Now tanh hx, let us assume it's equal to z, is given by sin hx by cos hx. Now using the division rule, d by dx of tanh hx is equal to the denominator cos hx into the derivative of the numerator, which is d by dx of sin hx minus the numerator sin hx into d by dx of the denominator cos hx divided by b square, which is cos hx squared. Now reducing this, now we know d by dx of sin hx x equal to cos hx, and d by dx of cos hx is equal to sin hx. So this will reduce to cos hx squared minus sin hx squared divided by cos hx squared, which is equal to 1 minus tan hx squared. But we have already assumed tan hx is z. So z is equal to tan hx. Therefore d by dx of tan hx is equal to 1 minus tan hx squared here, so which is equal to 1 minus z squared. So this reduces to a simple form that the derivative of the tan hx which is z is given by 1 minus z squared. Now as we know, the main objective of our neural network is to perform gradient descent and determine how the loss or the cost varies with respect to the changes in the weights in the hidden layer and the input layer and all the layers of the neural network. And then we can use the iterative gradient descent formula to arrive at the set of weights which will give us the lowest cost using gradient descent. So in the forward propagation direction, we have already seen the the equations as Z1, capital Z1 is equal to capital W1 into X plus B1, where W1 is the weight matrix and X is the input features, and A1 in at the hidden layer is equal to A1 is equal to tan H of Z1, the linear activation in the hidden layer, and Z2 at the output layer, linear activation output layer, is W2 into A1 plus B2, which you've already seen here, and A2 is equal to sigmoid of Z2, and then we know if you're doing binary classification, the loss is given as L is equal to minus Y log of A2 plus 1 minus Y log of 1 minus A2. Now we need to do backward propagation. As you can see, as you move in the forward direction, like Z is a function of X, then Z1 is a function of the input features, A1 is a function of Z1, and Z2 is a function of A1, and A2 is a function of Z2, and the loss is a function of A2. Now if you want to find how the loss varies with respect to the input features, we need to find all these derivatives and then use the chain rule so that we can arrive at the loss. And let's see how we do this. Now the loss is given as L is equal to minus Y log A2 plus 1 minus Y log of 1 minus A2. And we've already seen in part 2 that dL by dA2 is minus Y divided by A2 plus 1 minus Y divided by 1 minus A2, because d by dx of log x is 1 by x. And if now A2 is for binary classification, we are going to use sigmoid, so it's sigmoid of Z2. Therefore dA2 by dZ2 is A2 into 1 minus A2. We have seen in part 2 that the derivative of the sigmoid sigma is equal to sigma into 1 minus sigma. Now here instead of sigma we have A2, so it becomes A2 into 1 minus A2. Now let's find now Z2 is equal to W2A1 plus B2. Therefore dZ2 by dW2 is equal to dZ2 by dW2. This becomes a constant. If I take the derivative with respect to W2, it will be left with A1, and dZ2 by dB2, this first term becomes a constant, so it is essentially dB2 by dB2, which is 1. And then since let's A1 is equal to tan H of Z1, so dA1 by dZ1 is equal to 1 minus A1 square, because we saw the derivative of tan Hx is equal to 1 minus Z square. So using that we have 1 minus A1 square, and Z1 is equal to W1x plus B1. Therefore dZ1 by dW1 is equal to x, and dZ1 by dB1 is equal to 1. Now using these results we can find all the derivatives. Dou L by dou Z2 is equal to, using the chain rule, it's equal to dou L by dou A2 into dou A2 by dou Z2. Now dou L by dou A2 we already know it's equal to this one, which is minus Y of A2 plus 1 minus Y divided by 1 minus A2 into the derivative of the sigmoid, which is A2 into 1 minus A2. So if you multiply this and reduce it, you'll be getting A2 minus Y. Now we'll find dou L by how dou W2. That is one important result we need. Now this is equal to, using the chain rule, dou L by dou A2, dou A2 by dou Z2 into dou Z2 by dou W2. Now we have already in the above we have found out that dou L by dou Z2, which is this value, is A2 minus Y, and dou Z2 by dou W2, dou Z2 by dou W2 is A1. So we are left with A2 minus Y into A1, and dou L by dou B2, again this term is basically dou L by dou Z2, which is A2 minus Y, and dou Z2 by dou B2 is 1. So we are just left with A2 minus Y. Similarly, dou L by dou Z1 is dou L is a chain rule, dou L by dou A2, dou A2 by dou Z2, dou Z2 by dou A1 into dou A1 by dou Z1. Now dou L by dou A2 into dou A2 by dou Z2 is basically dou L by dou Z2, which is A2 minus Y. Dou Z2 by dou A1 is W2, and lastly dou A1 by dou Z1, that is the derivative of tan Hx, tan Hz1 is basically 1 minus A1 square. We have proved that. And lastly dou L by dou W1, again using the chain rule, is dou L by dou A2, dou A2 by dou Z2, dou Z2 by dou A1, dou A1 by dou Z1, dou Z1 by dou W1. Basically we notice this is basically whatever you got previously, and the additional last one is dou Z1 by dou W1. So we already have found out that up till this point dou L by dou Z1, it is A2 minus Y into W2 into 1 minus a1 squared, and lastly we only need to find dou z1 by dou w1, which is x. Dou z1 by dou w1 is x, and dou l by dou b1, again using the same chain rule, we have dou l by dou a2, dou a2 by dou z2, dou z2 by dou a1, dou a1 by dou z1, and dou z1 by dou b1. So dou l, this term is basically dou l by dou z2, which is a2 minus y. Dou z2 by dou a1 is w2, and dou a1 by dou z1 is the derivative of tan hx, tan h z1, which is equal to 1 minus a1 squared, and dou z1 by dou b1, basically it is basically this one becomes 0, and it is dou b1 by dou b1, which is 1. So it is basically 1. So this basically a2 minus y into w2 into 1 minus a1 squared. So the whole point of all this derivations, starting from the forward propagation and the backward propagation, was we were basically interested in these four results. That is, how the loss varies with the weights in the output layer, dou L by dou W2 and dou L by dou B2, also dou L by dou W1 and dou L by dou B1. Because we need these, because we can then use it in the gradient descent formula. So our forward propagation equation, and then once we have that, we can use it to implement our. So basically, we can use it in this gradient descent formula, where the weight I is the current weight minus alpha into the cost, how the cost changes with respect to the weight. So here we have found how the loss varies with respect to the weight, and I've already mentioned in my part 2 that the cost is the average sum of the loss over all the training samples. So once you find how the cost varies with respect to the weights at each layer, then we start with the random set of initial weights Wi and some bias. We do a forward propagation, that is, we compute these equations, and then we compute the loss, and from the loss we compute the average cost. And once we compute the average cost, we then compute how the cost varies with respect to the weights, and we use that to we do once, let's say we start with some initial weights, we do forward propagation, we compute the loss, and then we compute the total cost, and then with that weight, from that weight we substitute how the cost varies with respect to the weights which you have already computed, and multiply it by a small learning rate alpha, and we get a new set of weights. And similarly for the bias, we start with the initial bias, and we see how the cost varies with respect to the bias, and then subtract from that initial weight how the cost varies with respect to the bias, multiply by a small value alpha, and get a new set of weight. And then with this new set of weight, we do a forward propagation, compute the cost, compute the derivatives, and then subtract and get the new weights and bias, and then keep repeating the cycle. All of this can be easily done in languages like Python, R, or Octave, using because they all can handle matrices and vectors very easily by using simple implementation, which is shown here. Here this star is basically you multiply a2 minus y matrix into a1 matrix, the transpose here. So this is just the whole thing implemented in any language, R, Python, or Octave, and this basically implies it's element wise multiply. And so now that we have derived all the equations and we know how to implement this, we can easily implement it in any of these three languages. And we need to be able to adjust this alpha is known as the learning rate, and we need to adjust the learning rate so that we get the lowest cost. So now alpha is a hyperparameter which we have to manually choose, and we have to be careful in how we choose this alpha, because if we choose too large an alpha, then it may overshoot the minima, and if we choose too small an alpha, then it may take a long time to actually reach the minimum. So we have to choose appropriate value of the alpha. And again, this is just a computation graph. So basically, if it starts from the bottom to the top, so at the outmost layer we have the loss, then we compute how the loss varies with respect to the activation unit at the output layer, which we know as this. Then we compute the derivative of how dA2 by dZ2, which is since we're using a sigmoid, V A2 minus 1 minus A2. And if you want how the loss varies with respect to this dou L by dou Z2, then you multiply this output with this output, it reduces this. So it's just a way of visualizing the chain rule and how the derivatives are got for the weights and the activations at every layer. So this we saw was how the decision boundary when we use a two-layer network as logistic regression. Now if I do a simple three-layer network, I create a random cluster of data sets where the black denotes 0 and the yellow dots represent a 1, and I had my three-layer network to generate the non-linear boundaries between these data sets. And this is what I got for my Python implementation. You can see it has done a very good job of actually separating these yellow dots from these black dots. It has given three regions, and these stray yellow dots are fine because mostly it has generalized very well. So, and this I had chosen a hidden layer size with 4 activation units and a learning rate of 0.5, and this implementation was in Python. I took another data set I finally created where I created all the values within an inner circle is a 1, and all the values in the outside it is a 0. And I used a hidden layer size of with 12 activation units, just one hidden layer, and a learning rate of 2.2, and I get this nice non-linear boundary which is able to separate. And this is an implementation in Python. So this ends the second part of elements of neural network and deep learning. Thanks for listening.